Welcome to my class. Today we will discuss the circuit 4-bit adder subtractor. As the name suggests, it is a circuit which performs two functions: to add, and the same circuit will perform the second function to subtract. So it will add and subtract using the same hardware logic circuit. Let us understand what is the process of addition and subtraction. By using 2's complement. Before we go on to draw the circuit or the block diagram, let us first revise how we perform the function of subtraction a minus b. Subtraction of two binary numbers a and b, both being 4 bits each. We could write this as a plus minus b. So the operation being performed is subtraction, but the process being used is addition. If you recall, if this is a and you have to do a minus b, what you do is a plus minus b. To do this subtraction by addition, recall that if b was a number 0, 1, 0, 1, to find the 2's complement of b, which is nothing but 1's complement plus 1. So we first need to find the 1's complement of b. How do we do it? We just reverse the bits. So 1 becomes a 0, 0 ka 1, 1 will be 0, 0 will be 1. So the 1's complement of b will be 1, 0, 1, 0. Just the opposite of this one. 2's complement of b will be this 1's complement plus 1. So that will be 1, 0, 1, 1. Now this is nothing but representing the negative binary number minus b. Recall that 1, 0, 1, 1 is the 2's complement representation of the negative number minus b. So coming back over here, if our example was of a number 1, 1, 0, 1, we perform this operation by writing a as 1, 1, 0, 1, adding minus b 1, 0, 1, 1, 1, 0, 1, 1, and now the operation that will be done is nothing but a simple addition of 4 bits each. Remember that we had labeled these bits as A0, A1, A2, A3, B0, B1, B2, B3, and we perform the operation of addition. The first bit added A0 and B0 gives 1 plus, and there is a carry in from somewhere. If we assume that as 0, it will be 0, 1 plus 1, 0 with a 1 carry, 1 plus 1, 0 with a 1 carry, 1 plus 1, 0 with a 1 carry, 1 plus 1 plus 1 will be a 1 with a 1 carry. And if you recall the 2's complement process, this carry is ignored. You ignore the carry or you drop the carry. And this gives you your final 4-bit sum. Now this process has to be implemented with the logic circuit. The logic circuit used for that, if we first visualize the block diagram, as always, we first will draw the block diagram for the 4-bit parallel adder subtractor. The same circuit will perform both the functions. So it will be a circuit which will 4-bit having it will perform two functions, a plus b, and it will also perform the function a plus minus b. The first function being the add function and the second being the subtract function. As in the parallel adder, the A is a 4-bit number. Similarly, the B is another 4-bit number. If we write these as, label these as A0, A1, A2, A3, and B0, B1, B2, B3. This is the 4-bit number B, and this is another 4-bit number A. As earlier, the output will be a 4-bit sum because the circuit is performing the function of S0, S1, S2, S3. It is performing the function of addition to perform add or subtract operation. A carry is generated as Cout, and there is another carry which is the input carry in. Cout is the Cin is the carry in, and Cout is the carry out. Up till here, this circuit is identical to the 4-bit parallel adder, which was doing the function of A plus B addition. Now, if the same circuit needs to perform two functions A plus B, in this case, there will be another input which will be called as the M input, which is the mode control input. And the function of this mode control input will be, if M is 1, when M is 1, the circuit will perform the operation of subtraction. And when M is 0, the same circuit will perform the function of addition. So this is the role of the mode control input. One mode control input will be required to allow the circuit to function in two modes. So what are those two modes? We may write those modes as when M is 1, the circuit performs the function of subtract, and when M is 0, the same circuit performs the function of addition. And this mode line M is coming from the circuit controller or the CPU. Okay, with this clarity in our mind, we see that the circuit will be very similar to the 4-bit parallel adder. From a previous chapter, just recall that the circuit of a 4-bit parallel adder had 4 full adders: full adder 0, full adder 1, full adder 2, full adder 3, and the full adder 1 was doing nothing but A0 plus B0. The next full adder does A1 plus B1. The next was doing A2 plus B2. And this was doing A3 plus B3. And recall that the carry out of the first going as carry into the next, carry out of 1 going to carry out of 2, in of 2, carry out of 2 going as carry in to 3, and final carry of FA3 coming out as the final carry out. And this is the carry in coming from a previous column. So up till here, the circuit is identical to the full adder, the parallel adder. Now, just like we saw that in the block diagram, there is a very minor change. This was the block diagram. There's a one minor change of the mode control input being added in a manner so that when M is 1, the circuit subtracts. When M is 0, the circuit should add. To implement this in the logic gates and the hardware of the adder subtractor circuit, all that needs to be done is in the B input, an additional gate. If you see this, can you recognize this gate? This is an XOR. So in every B input, if there is an XOR gate connected like this, the B input is passing through the XOR gate. So there is one XOR gate each for the B input. Because why for the B input? Why not for the A input? Because it is the B input which is to be complemented. So this B0 is coming from here, this B1 is coming from here, B2 is here, and B3 is here. So we cross these. Okay, we leave this like this. So these are the B input, and what does this function need to do? A0 plus 0, or it has to do A0 plus minus B0. This adder has to do A1 plus minus B1. FA2 will do A2 plus minus B2. And FA3 will do A3 plus minus B3. From where do you get the minus B? Remember that the minus B was obtained by first taking the 1's complement of B, adding another 1. Gives you the 2's complement of B. Before we complete this circuit, we will have to see the role of this XOR gate. In this combination, the XOR gate, it used as a controlled inverter. Controlled inverter. What do we understand by controlled inverter? Recall an XOR gate having the inputs A, B and the output Y. If you just recall the truth table of the XOR gate, a 2-input XOR gate having the 4 possible combinations 0, 0, 0, 1, 1, 0, 1, 1, and the output would be this. Do we all remember? This is a simple truth table of an XOR function. 2-input XOR. Now you just see that if in place of A, I call this input not as A but as M, which is your mode control input, and we try to see how this gate is behaving when M is 0 and how does it behave when M is 1. From the truth table, you can see that these are the 2 combinations. Now, if I call this A as M, these are the 2 combinations when M is 0, and these are the 2 combinations when M is 1. So you may see that in both these combinations, when M is 0, what is happening? If B is 0, output is 0. If B is 1, the output is a 1. So what are you getting the output in this case? The output in this case is the same as B. If B is 0, Y 0, B 1, Y 1. Now let us see what is happening when M is 1. See that when M is 1, when B is 0, the output is a 1. When B is 1, the output is a 0. So we may say that in this condition, the output which is coming is nothing but minus B, which is the 1's complement of B. 1's complement of B. The B is just getting inverted. Let's just put the values over here and see. When M is 1, if B is 0, then 1 and 0 gives a 1 output. So this B is inverted. Let us see what happens when M is 0. When M is 0 and you assume B as 0, then 0, 0 gives a 0 output. The output is 0 and there is no change in the output B. This is the same as B. In the earlier case, this minus 1 was minus B. 1 was minus B. This is how the XOR gate is working like a controlled inverter. When the input M is 0, Y goes as direct, Y is B or simply as plus B. When M is 1, the output, what is Y? It is our output. Okay, this is the function of the XOR gate as a controlled inverter. So now let us come back to our diagram of the adder subtractor. The line M, mode line, is, we saw that our A line will be called as the mode line. So where we have our A's, the A input, that is all connected together. And Oh, we made a mistake here. I'm sorry.